Hi, everyone. I'm Bingchen Zhao, and I'm the session chair for the morning session. For the morning session, we have 3 invited talks. 2 of them are pre-recorded, and one is live. One is a live talk. And then followed by a short break, we'll have the post session and the challenge winner announcement. So for the first invited talk, we have Professor Pietro Perona from Caltech. Professor Pietro Perona is the Allen E. Packett Professor of Electrical Engineering and Computational and Neural Systems at the California Institute of Technology and the director of the National Science Foundation Engineering Research Center in Neuroformic System Engineering. He's known for his research in computer vision and is the director of the Caltech Computational Vision Group. His talk will be pre-recorded, so if you want to ask him questions, you can attend the panel discussion at the end of today to ask him questions. So now, okay.
So good morning, everyone. I'm talking to you from California. So first of all, thank you to the organizers for inviting me, and many congratulations to the winners of the competition. And so today we want to think about generalization, and so I thought I would share some thoughts and share some recent results, and let's see how that goes. So give me a moment to share my screen. Here you go. Okay. So first of all, this workshop is here because we don't know how to generalize, and this is a picture that appears in a paper by Sarabiri from a couple of years ago, where I tried the clarify system on these 3 pictures of cows, and as you can see, the left picture is classified correctly. Clarify thinks that cow is really there, but the other 2 pictures are a big problem. And what's happening is that the pictures in the middle and the right are not typical pictures of cows, and there are cows in new environments, and therefore the system is confused. So this gives you the impression that current systems do not really see the objects, don't learn the objects, but learn just a conjunction of features. And that's, of course, a big problem. Now, our visual system is much better. So I'll show you these objects. I'll ask you what they are, and you will tell me, of course, that they are bicycles. Now, it turns out that these bicycles are not real bicycles. They're built by an artist who asked students to draw bicycles, and he was impressed by the fact that people draw bicycles in ways that are completely unnatural. And so these bicycles, the shape and the mechanical parts and so on are completely wrong, and yet we have no problem recognizing bicycles. So from our training set, we humans seem to be able to generalize very well, even to things that don't exist, and so we couldn't possibly have ever seen. And the impression is that current deep networks need instead to learn by rote, and these are examples of chickadees, and they're in many different poses, and unless the algorithm sees the chickadee in all the possible poses, then it's in trouble. And now we see this in our experiments, and so here we go back to the experiments of Sarabiri in her 2018 ECCV paper. And what we see here is 2 important things. One is that when the number of training examples is large, 10 to the 4 on the extreme right of the monitor, then the performance is extraordinarily good, about 1% error rate in classifying these animals. But when we have, say, 10 training examples, then performance is terrible. The error rate goes up to 80%. Now, by contrast, humans may not be as good as our algorithms when we have lots of training examples. We have seen algorithms that beat experts at their own game in dermatology, in recognizing birds and animals and plants. when we have 10 to the 4 training examples per category, but humans are much more efficient. And so when n, which is the number of training examples, goes down to 0, humans still make very few errors. They can be trained easily, especially if they are already experts. But our algorithms are in trouble. So what can we do about this terrible situation? And of course, you guys have come to this meeting because you have ideas. And in thinking about it, it seems to me that there are 4 possible approaches. One is to continue collecting more training data, and so just keep feeding training data. We seem to see that networks errors are going down as we increase the number of training examples. So certainly that's an approach. The second approach is to think of better architectures, and we've seen a flourishing of new ideas with transformers, for example. The third one is to push for unsupervised, semi-supervised, self-supervised algorithms that can make use of a wealth of images that you can find on the internet, but don't require so much annotation. And what I will argue is that abstraction is something we should pursue, and I'll make it clear in a moment what this means. But first, let me try to convince you that the first 3 approaches are maybe not so hot, and we need to really think harder. So first of all, really, do we need more data? And this plot is taken from the iNaturalist archive paper from 2017. And we see the state of the published iNaturalist data set at the time. And so we have about 5,000 species, and that's the x-axis. And for each species, we have a certain number of exemplars. And so from this, you see a couple of things. One is that, current, as we all know, current data sets have tons of examples. So the full iNaturalist training set is probably 30, 40 million images with 50,000 species. But we have long tails. And so indeed, no matter how hard we try, we'll never be able to collect lots of images for most of the species. And so here you see that from species 1,000 onwards, we have fewer than 100 training examples. And from species 2,000 onwards, we have fewer than 30 training examples. So no matter how hard you try, there are always going to be things that we don't see very often. And so collecting lots of training examples is not practical. And even if we did, we know that the generalization is difficult. And this is, again, the paper from Sarabiri, which uses camera trap data. And so since the training examples are highly correlated because they come from a handful of camera traps, generalization to new camera trap locations, which have different statistics of images, is very hard. And so you see it on the left is the performance curves, log error versus log number of training examples for locations where the training set was collected. And so the blue curve shows you the error rates for images that are classified, and the red one when you have bounding boxes around the objects. And you see that the curves are far higher, so much more error on the right-hand side when you measure performance on cameras that did not provide training examples. And so that's a conundrum that we are facing. And so more data in many situations where the data is highly correlated, like in industry for inspection and camera traps, more data may not even be so useful. Now, the second approach was to think about new architectures. And there is a nice paper by Musgrave et al. With the senior author is Serge Belongi, showing that since 2016 until now, we have very little, if no progress at all, in the performance of algorithms. And so here the colored bars are different data sets, different test sets. The vertical axis is the accuracy of different architectures. And so each group of 3 bars is a new architecture that was introduced through the years. And what they say is that if you train these architectures, even the new ones, using the same care, the performance of the old ones and the new ones and different learning algorithms and so on doesn't change. And so we don't seem to be very lucky with new architectures. Of course, we have to keep pushing on this. Now, will self-supervision help? And here is a paper by Eli Cole and others that came out at CVPR 2022 this year, showing that those self-supervision algorithms like SimCLR that seem to be doing very well on ImageNet don't seem to be doing well on other training sets, on other sets like iNaturalist. And so the picture is a bit complicated, but what is important is that the black curve is supervised and is doing much better than the self-supervised approaches, even when you have 1 million images, which would be the orange curve for self-supervision. And if you especially go to low number of training examples, the accuracy is abysmally low for all of these approaches. So we don't seem to have self-supervised approaches yet that can do a great deal of good. Now, one thing that makes me think is the picture, the initial picture with the cows. What I'm thinking is the algorithms are truly not seeing the cows. And what does it mean to see a cow? It means to identify all the parts of the cows and know where the eyes, the ears, and the back and the tail and the legs are. And this is where people were about 50 years ago. And so you see on the left the picture from a paper by Fischler and Elschlager, and their point of view on how you should detect faces is that you should define different parts, the eyes, the nose, the mouth, etc., and impose that they come at a certain mutual position. And so the idea was detecting the parts and then making sure that the parts are in the correct mutual position, and then you have detected an object. Now, we have abandoned that point of view in favor of learning approaches. And here on the right, you have the cognitron that appeared more or less at the same time by Fukushima. And so why have we done that? Well, because we don't want to hand engineer each model that recognizing an object. And so the Fischler and Elschlager was handcrafted. And so if we want to handcraft approaches for the millions of categories that we have to face in the world, that we will never be done. And it's also, we know that the data speaks louder than experts, and so the learning approaches are both better, but they have the problems that we were talking about before. Now, if we go back to the early 2000s, there is work from my group that showed that you can in fact have learning approaches that discover the different parts of objects, and therefore then objects can be detected in pictures against completely different backgrounds. So naturally, those algorithms don't stack up against current deep network algorithms, but they have this idea that you can learn an abstraction, which is learning the different parts and their mutual positions. And so my inclination would be to go back and revisit that kind of literature and see if we can combine it with current learning approaches. And so here I'm showing you pictures from Rob Fergus's thesis, but this research started earlier in 95, 98 with work by Pearl, Leong, and then later Feifei and Fergus and Max Welling, etc. Okay, so now another benefit if we discover parts of categories is that we can establish a language with our experts, the ones who are producing the training sets. And so here I want to give you an example of what could happen. So these are pictures of bees that I took. I have a beehive at home, and I was wondering if a certain parasite called the varroa mite is present in my bees. So I took lots of photographs, and I thought I should train a computer vision algorithm to detect it. But the problem is that I could only find by hand 3 examples. And so we know that this parasite cannot be found by our algorithms because I don't have enough training examples. But I can train you very quickly with a sentence to find it. And so the varroa mite looks like one of the bee's eyes. And so you know what the bee's eyes are, but it's red and it's stuck to the body of the bee. And so by now, some of you in the audience will have seen it. And for those who haven't seen it, it's there. And so with one sentence, I had the same effect as probably thousands of training examples of varroa mites. So it looks like if we know about parts and attributes and visual features, we can establish a language for the annotators that is much more effective than just drawing bounding boxes on images. So if we revisit the ideas that we wanted to pursue, I think better architectures is still a bit of a question mark. Are we able to come up with better architectures? I don't know. Now, more training data, I would say, let's not pursue that because of the reasons I said, namely not good enough, long tails, and difficulty in generalization anyway. Now, unsupervised, semi-supervised, self-supervised, I mean, it's great, but it doesn't seem to be yielding results for the moment. And I may be slightly too pessimistic, but anyway. And so I want to pursue a little bit the question of abstraction. And so today I want to show you a few slides on a recent paper by my student Nihar Kondapaneni that illustrates a couple of ideas. And so hopefully I'll show you those slides and we'll get ideas and we'll close with that. So the abstraction that Nihar is trying to learn automatically is the one of natural numbers. And it's an interesting abstraction because it's at the foundation of mathematics. And if you ask a mathematician, what is a number? They say, well, numbers are equivalence classes between sets. And so if a set, if you can put in one-to-one correspondence, all the elements of one set to all the elements of another set, then they have the same number of objects inside. And there are very interesting relationships, like not only there is the abstraction of how many objects there are, but also we have an ordering of these numbers. Now, it turns out that although you can think of this abstraction as completely mathematical and linguistic, in fact, it's very connected with vision. And this psychologists know it. And so they talk about numerosity, estimation, and subitization. So if I ask you how many buffaloes you see, you would say one. You have no doubt it's immediate. Well, if I ask you how many birds you see, you say, well, maybe 6 or 7, something like that. You're not completely sure, but you get ballpark right the estimate. And if I ask you how many bees do you see here, you will say about 15 or 20, and it wouldn't be very far from reality. So the abstraction of numbers has an ordering, but then also it's very deeply rooted in perception. And the question is, can we learn this abstraction from images without supervision? And so that would be a place where we want to go. And so is a teacher needed? Like this boy, is he able to learn numbers without somebody telling him about the numbers? And so here you see a video. I hope that the video is visible in YouTube of myself doing what I think a child is doing when they are 2 or 3 years old. And they play with the object and they pick them, place them. So you imagine that their motor system is developed. They can pick and place objects, but they don't know about numbers. And so my claim is that just by playing with an object like this and watching what they're doing with their hands, they can learn the abstraction of numbers. So the way I think of it is that there are 3 actions that the child can do. One is to put an object into the workspace. Another one is to take an object away. And the third one is to shake the objects to change their arrangement. And so in order to explore this question, we're actually not using tomatoes for the moment. We're using artificial pictures with synthetic blobs that represent the tomatoes or the objects. And look at the bottom row. You have different pictures and the actions of put, shake, and take were applied. And so you have more or fewer objects. And the objects can vary from image to image in position, in contrast, and in size to mimic what could happen if you change lighting and if you change a little bit the position of your head, etc. And so what we would like to do is by playing with objects, we'd like to come up with an embedding using perception, which maps images that contain the same number of objects, like the second and the third row here, into the same place in an embedding and images that contain a different number of objects into a different place in an embedding, despite the fact that the images that contain the same number of objects are quite different one from the other and may be more similar to others that contain a different number of objects. So after the embedding is made, then you can associate the name for these, to these categories, and that's a different story. But the question is, can you come up automatically without supervision with an embedding that abstracts away the number? And so how could you do it? Well, we know how to train a network that computes an embedding and then a classifier. The trouble is that this is not the right structure because we want to learn about numbers without supervision, and this point of view is a supervised point of view where you would use learning to correct errors in the numbers, but the numbers have to be known for each scene. So that's not what we want to do. So the only thing we know are the three actions of put, take, and shake. And so this may be the way to go, that the classifier classifies put, take, and shake. But of course, this doesn't work either, because to judge if there was a put, a take, or a shake, you have to have two images and not one, the image before and the image afterwards. And so the way to think about it is to have a Siamese network that does perception, where the previous image and the current image are being analyzed and projected into the embedding. And from the embedding of before and after, an action classifier will classify the images. Okay, so now we have some scheme that we can use to train with supervision. And here it's shown in a slightly different way, where the world is below, there is a hand moving objects, and there is perception. Those are eyeglasses producing a representation that's embedding. And the classifier has to compare it to embeddings and decide if the action of take, put, or shake was taken. And you can implement all of this in a very simple way with, any one of you would be able to implement it in maybe half an hour. It would take me half a week, but for you, it's much faster. And so if you look at, if you train the system that predicts which action was made, you can see that it does well within the set of the training set. So if you have up to 3 objects, and the number of objects is along the x-axis, the error rate in predicting the actions is very low, around 1%, given a certain training set. However, as you would expect, when the number of objects is more than the ones that were in the learning set, in the training set, the error rate goes up. Now, how big is the embedding that you need to do this? Well, it turns out it's surprising. It's the dimension is 1. And you see it in the plot below, where the dimension of the embedding does not influence the error rate when you train and test on scenes from 0 to 3 objects. Now, this is a surprise, and more surprises come when you look at the representation, namely the embedding. And so what I'll show you is the embedding you obtain if you use 2 dimensions for the embedding. And again, you train with scenes containing from 0 to 3 objects. And so this is each dot here, and the dots are near each other, so they look like all a group, but each dot here is an image containing between 0 and 30 objects. So although the system was trained with up to 3 objects, here the images contain up to 30 objects. And what you see is that there is a tremendous regularity. So instead of the images being scattered around all over the place in embedding, they're arranged along a line. And that's interesting. And the line seems to have an ordering, because what you see is that the images are color-coded. Lighter blue is images with few objects, and darker blue is images with more objects. And you see that they are all sorted out, okay? And so the system seems to have learned that the size of or the number of objects in a picture. And there is one more surprise. If you look at the extremum of low number of objects, you see that these dots are grouped into islands. And if you analyze the groups into islands, you realize that each group corresponds to a scene containing a certain number of objects. And so I don't have the time to go through in detail of these pictures, but the top right island, which if you see my mouse, it's here, contains only 0 objects. The green island contains 1 object. For all the scenes that map here, contain 1 object, 2 objects, 3 objects, 4 objects, up to 6, and then it's many, if you will. And now, so what you see is that basically this representation allows a system to estimate the number of objects in a scene. And it also estimates precisely, so while quantity estimation here is not precise, it can estimate precisely the objects from the scene, the number of objects in scenes from 0 to 5 or 6 objects. And so this is a comparison with human psychophysics. And what you find is that both the absolute judgment of the number of objects in a scene and the relative judgment, which scene contains more objects between the center, left, and right, they mirror. The model is this blue line and this bluer line here, and it maps very close to reality, which is the perfect performance would be the red line, and within the realm of human performance, which is the shaded green area. So what have we learned? And so what we see is that indeed there are situations where abstraction can be learned without supervision. And in this case, manipulation, which is picking and placing objects, is teaching perception about abstraction. Now, what is crucial here is multimodality, namely there is manipulation and there is perception, and they're interacting to produce an abstraction. So what I'm proposing is that maybe we should look beyond our current batch training sets and think about video and think about multimodality for training our systems. And maybe we can come up with stronger abstractions that will help our algorithms generalize beyond the current, the statistics of the training set. And we see strong extrapolation here because if you remember, the ability of the system to estimate quantity goes far beyond the initial 3 training examples, the 3 objects in the training set from 0 to 3, which would be up here. And this embedding can estimate quantity up to 30 and beyond. We have not tested beyond. And also it can estimate the exact number of objects up to 6. So even if you have 0 to 3 objects in the training set, well, you get an exact number up to 6 or 7 in this case. Okay, so I'm done. Thank you for your attention. And you will find this paper on arXiv, and this is a picture of Nihar Kondapaneni, the student who was involved in this project. Thank you.